So let's our continue our discussion on refraction. So far we have discussed about refraction through plane surface. Okay, so where we have studied the various the phenomena laws about the plane surface. The next important part is for the spherical surface like the lens. Okay, so these are the core topics in the refractions. So why the convergence and divergence take place in case of lens, and the relations, the formulas, the lens maker formula. So let us going to discuss in this particular discussion. So today's discussion is on refraction through spherical surface. See, the best example for the spherical surface is the lens. Okay, so in lower class you studied about various type of lens here. Okay, so this is one type of the lens. See, the material made up of some transparent medium. So this is the second type of lens. Okay, so this is the third type. Okay, so this is one more here. Okay, so these are the various types of lens here. Inner one is a denser medium and surrounded by a rarer medium like that. See, this particular lens we call it as, okay, it is called as convex lens or double convex lens. This particular shape of the lens is called concave lens. Okay, so this one is called, you can see here, the one surface is plane and the second surface is curved. It look like convex surface, therefore it is called plano-convex. And this is, again you can see here, one is plane and second is the curved. So this is called plano-concave. Plano-concave, and you can see here, now this is, one is concave and second is the convex. This is called concave-convex. Or if you take the mirror of this particular lens, then it becomes convex or concave like that. Now this is various type of lens here which you are going to study in next consecutive lectures. Okay, so to study this lens, okay, so we require certain fine formulas. We have to derive the relation between the refractive index and other geometrical quantities. Then only we are going to have a clear picture about the lenses. Okay, so let me define lens here first of all. So what is lens? What is lens? You can see here, lens is a transparent medium. It is an optical medium. Okay, lens is nothing but an optical medium, but you can see here, the surface should be, they should not be plane. Okay, if they are plane, you can see here, this is a plane, then the phenomena is different. If light passes through the plane glass slab, then the lateral shift take place, okay, or the normal shift take place. We already discussed in the previous lectures. Okay, so this time our mediums are not plane. This time the medium is a curved one, okay, a spherical one. So this particular type of arrangements we call it as lens. So let me define lens. What is lens? So lens is an optical medium or transparent medium. Okay, optical medium bounded by, okay, surrounded by, bounded by what? Bounded by at least one spherical surface. You can see here there are two spherical surfaces here in case of convex and concave. In the plano-convex and plano-concave, there is only one spherical surface is there. Still we call it as lens only. Okay, so therefore we define like this. So lens is an optical medium bounded by at least one spherical surface. At least one spherical surface. Okay, bounded by at least one spherical surface. So that is called a lens. So this is the geometrical quantities here. Okay, so the optical quantities are the refractive index, to study the behavior of lens. Okay, so you have to relate with respect to refractive index. Now this is one quantity. The second quantity is the geometrical factors. For an example, if you take a convex lens, you can see here. Okay, so this is a convex lens. Okay, so we consider that convex lens is an what? Now you can see here. If I okay, so if I make some imagination here. Okay, let us imagine that we have the two spherical glass spheres and they are coincide, they are intersecting. No, so this is not possible. If you want to coincide the two spherical glass surface, definitely they get breakdown. Let us imagine that. Okay, so you are trying to you have intersected two spherical glass sphere. So this is one spherical glass sphere, one. This is second glass spherical glass sphere, two. You can see it when two spherical glass sphere intersected. So if you take this particular shape, that intersected part is nothing but an convex lens. Okay, so therefore we consider that the convex lens is the intersection of two spherical glass spheres. Okay, see, this is first spherical glass surface which is corresponding to this surface. If I call this surface as A, B, C, so this ABC is the part of the first spherical glass sphere, and this is ABC is the part of second glass spheres. So which are the geometrical factors here? You can see here. So this is ABC is nothing but what? This is the spherical part. This is part of the first sphere, and the first part of the sphere we call it as curvature. Okay, so therefore nothing but ABC is nothing but the curvature of the first imaginary sphere. So you know that sphere has got certain center and sphere has got certain radius. But you don't have this entire sphere here. Now this ABC is nothing but is the part of the first imaginary sphere. Therefore, this part is called curvature. Therefore, we call C as not center of the sphere. We call it as center of curvature. Okay, center of curvature, and particular this distance is called radius of curvature. Similarly, if you take on the other side, if you take ABC, is again it is the part of an imaginary sphere 2. Again, this sphere has got certain center as well as it has also got certain radius. Okay, therefore, a particular convex lens has got two center of curvatures and two radius of curvatures. So this is the geometry here. Okay, so this particular convex lens has two radius of curvature as well as two center of curvature. So now these are the determining factors in case of formation of images. Okay, if they are the radius are equal, then we call it as equiconvex lens. Okay, so these are the factors which determine the distance, the measurements, okay, and the phenomena corresponding to ray optics about the lenses here. So now this is the first geometrical factor. So before going into the lens, okay, so this is nothing but, so what is lens? Lens is nothing but intersection of two a spherical surface. So in this particular lecture, first you have to discuss about one surface. Okay, so in this lecture we are going to derive the formation of images, formation of image, and the relation between optical quantity and geometrical quantity in terms of one spherical surface. Okay, we are going to make one fine formula here. In the next lecture, what we do is we are going to study the entire lens. This entire lens is nothing but it is made up of two spherical surface. Okay, if I have the formula for the spherical surface, then what we do is first we are going to apply the formula for the spherical surface for the first surface by assuming that second surface is absent. Then we are going to apply the formula for the second surface by assuming that the first one is absent. Then we combine we are going to get an formula. That beautiful formula is called lens maker's formula. Okay, so before lens maker's formula, let me derive the relation which connect optical quantity and the geometrical quantity for an single spherical surface, and that is called refraction at spherical surface. So this is our first discussion. Refraction at spherical surface. Okay, refraction at single spherical surface. Okay, we are going to study at single spherical surface. Then we are going to study about lenses here. Okay, so single surface. So let me take a single surface. So this is a single surface. Okay, so we don't know what is an surface on the other side. Okay, I have taken only one part of the lens. Okay, one part of the spherical surface. Now this is the entire sphere. We have taken only a part of the spherical sphere. So you know that the sphere, if I take the, okay, so if you draw the entire, okay, so if you take the entire shape here, then that is nothing but a sphere, and sphere has got certain center of curvature. So let me call the center of curvature as C, and this particular distance is nothing but radius of curvature. So this is center of curvature C, and this is radius of curvature R. And you know that, okay, so the geometrical point of this spherical surface, we call it as pole. So this is the pole here, and the line which passes through the pole and center of curvature. Now that particular line we call it as what? This particular line is called principal axis. Okay, so same notations as we use in case of the refraction through spherical mirrors, because it is spherical surface only. Okay, so somewhere here it is a pole is there. Okay, so this is a denser medium. Okay, so this particular region is a denser medium. Okay, you know that on the other side, see, this is a part of the sphere, so it is made up of some glass like this. So this is a denser medium, and this one is the outside one. It may be air medium, or it is a less denser medium. So if I take the refractive index as of this medium as N2, and let me take the refractive index of outside medium as N1. Okay, so light passes through the transparent medium, refraction take place. If refraction take place, then it has to obey the Snell's law, and Snell's law gives the relation between angles and refractive index. Therefore, I am mentioning the refractive index of the medium. Let me assume that, let me consider that N2 is the refractive index of the medium which contains the spherical surface, and N1 is the surrounding medium. Okay, so let me take a point object for the sake of discussion. Let me take a point object as, so this is a point object, so let me call this point object as O. So O is the point object. See, so the first ray, it passes through the principal axis. You know that when it passes through the center of curvature, it passes through the pole, it is undeviated. Is I is equal to R, the R is also, if I is equal to R 0, then R is also 0. It is correct. Okay, so if it is normal incidence, then I is equal to 0, then R is also 0. What is meant by normal in case of spherical surface? Okay, if you take the sphere, if C is the center of the sphere, if you take the radius, you know that the radius is always perpendicular to the surface. In previous lectures also we have assumed that, see, this, if you take this entire shape, then it is nothing but a sphere. If you take a very small part, infinitesimally small part of the surface, then it looks like plane. You can see here, it looks like an plane. If you take a small part of the sphere, it looks like an plane, and that plane is perpendicular to what? Radius. Therefore, radius is nothing but normal in case of spherical surface. Okay, so the radius, so it is normal, the line which is perpendicular to the surface. And which line is perpendicular to the surface? It is the radius. Therefore, the line which passes through the radius is nothing but normal. So you can see here this particular line, it is passing through the center of curvature. So this is nothing but radius. So therefore it is nothing but the normal. Therefore if I is equal to 0, then R is also 0. So your first particular light, it passes through the spherical surface undeviated. Okay. So let me take a second one. You know that for the formation of images, at least two rays are required. Let me take a second here. Okay, so this is the second one. It falls on this particular point. This point is called point of incidence. So this is called point of incidence. Okay, so what happens? Now here again, if I draw the normal, what is normal? The line which is perpendicular to the surface. Okay, so this is normal here in this case. Okay, this passes through center of curvature. It coincides on M. So this particular line is nothing but radius. So that is nothing but normal. So you know that when light travels from rarer medium to denser medium, it bends towards normal. Okay, so it bent towards normal. As it bent towards normal, you can see here this particular light, it get refracted, it bent towards normal, and finally it is going to coincide. These two rays which are coming from an object, both are going to intersect at a particular point on the principal axis. That point is called image. Is it clear what is object? If from that particular point, if the rays are diverging from that particular point, then that point is called object. And what is image? After refraction, if the rays are going to converge on the particular point, then that point is called image. If the light diverges from the point object, if light converges to a point, then it is called image. So this is object, and this is I is the image of the object O. Okay, so you know that. So this particular point is nothing but what? So if I take this one as P, P is nothing but a pole. So therefore this distance, the distance between the object and the P, this particular distance is nothing but what? This distance is called object distance. The distance between object and the pole is nothing but object distance. It is represented by U. The distance between pole and C is nothing but what? So this distance is nothing but radius of curvature R, and this distance, the distance between image and the object, is nothing but image distance V. Is it correct? Okay, so now discussion is we have to relate the relation between, we have to make a relation which connect between N1, N2, U, V and R. Okay, so if I derive that particular relation, then other things are very easy. Now this is a purely geometry here. Okay, so some one missing factors there. Notice here. So if this is normal, so this is the incident ray. So this one is normal. So this, therefore this particular angle becomes what? So this particular angle becomes angle of incidence I. Again you can see here. So this is what? Okay, you can see here. So this is I. So this angle between the refracted ray and the normal is nothing but R. Okay. See, for sake of discussion, we make one geometrical construction here. What is a geometrical construction? What we do is we simply, okay, so we drop a line from M so that it meets at some point on the principal axis. Let me call that point as N. Okay, so as we discussed in the earlier lecture, so the spherical surface is it's only a very small part here. Okay, so this aperture, this entire aperture, actual size is somewhat like this. It is very small. Okay, so that this, if you draw the ray diagram, so somewhat it look like this. For the sake of visibility, okay, so we can't take such a small, okay, so the size of the ray here, if you take like that, it is difficult to derive the, okay, so the we can't write the small parts here, therefore simply we enlarge this image. Are you getting me? So therefore I can see here, actually this P and N, they are very close to each other. They are not far from each other, they are very close here. So therefore we assume that OP is nothing but ON. CP is nothing but CN. Okay, this distance is very small. It is almost, it is negligible. Okay, so this is an, okay, you have to consider like this, otherwise it is difficult to derive. Okay, so we take that this aperture is very small. These angles I and R, they are very small. This particular angles you can see here, this something look like 45 degree, but actually they are not 45 degree. They are around, simply they are less than 10 degree, less than 5 degrees. Okay, so what is your aim here? We have to derive the relation between N1, N2, U, V, R. We have to connect the geometrical quantities with the physical quantities. Okay, so for that we are taking the help of the geometry. Okay, simple geometries here. So if the refraction take place, it should obey Snell's law. It should obey the law of refraction. The first law of refraction says that your incident ray, refracted ray, and normal must lie on the same plane. Yes, it is true. And second one is it should obey Snell's law at the refracting surface. Okay, if it obeys the Snell's law at the refracting surface, then only we can say that the light has undergone certain refraction. Therefore, okay, let me start here. Apply Snell's law at the surface. Okay, apply Snell's law at the surface here. For this particular surface, let me apply the Snell's law. What is Snell's law? Says that N1 sine of I is equal to N2 sine of R. Is it correct? Refractive index of the medium into sine of angle in that medium, that should be equal to refractive index of other medium into sine of angle in that medium. Is it correct? So you can write N1 into sine of I is equal to N2 into sine of R. But here, as I already said, that this I and R are very small. Okay, so if you take the actual figure is somewhat like this. It is not, okay, bigger in size. Actually, the actual size is like this. So if you take the I and R, you can see here they are very small. These angles are very small. Therefore, if angles are small, if I is small, then the trigonometry says that sine of I is equal to I. Okay, if angles are small, then tan of I is equal to I. This is not true in case of cos, but in case of sine and I, we can say that if the angles are small, if it is theta, if theta is very small, you can say that the sine of theta is equal to theta, tan of theta is equal to theta. If theta is 0, what is sine of theta? Sine of theta is also 0. Therefore, I can say that sine of theta is equal to theta if theta is very small. It is around 0 degree. You can say that the tan, same is for tan. If theta is 0, tan of theta is also 0. Okay, so therefore now I can write like this: N1 sine of I is equal to N2 sine of R. It can be written as N1 I is equal to N2 R. Angles are very small, therefore we can say that instead of sine I, we can simply write I. This is true only when angles are small. Okay, therefore N1 sine of I is equal to N2 sine of R. Therefore, I have taken a physical quantity, that is N1 and N2. Okay, we have to relate N1 and N2 with respect to UVR. And you can see here UVR, they are related to some triangles here. Okay, so they are in between certain triangles. Therefore, I have to replace that I and R by, okay, so we have to in between we have to make an the arrangement in such a way that we can replace that I and R by U, V and R. Now see here, what you do is, so you can see here M, N, O. Okay, so M, N, O. It look like a right angle triangle. Therefore, I can write in M, N, O, or in triangle M, N, O. You can write here tan of angle M, O, N. The first angle. Okay, in that particular angle we have the value U. Okay, therefore I have taken the angle MON. So tan of MON, tan theta. Tan theta is nothing but opposite side divided by the adjacent side. Therefore it becomes MN by, okay, you can see here MN by NO. Okay, similarly, if I take the triangle, so NO is nothing but U. So we have introduced U in this particular figure like this. So let me take the next triangle as MNI. If I take the triangle MNI, then if you take the tan of MIN, tan of MIN is nothing but, in this case tan of MIN is nothing but opposite side is MN by NI. Okay, similarly, let me take the third triangle MCN. Again, it's a right angle triangle MCN, and tan of, you can take this angle as tan of MCN is equal to, you can write MN by NC. Okay, this is correct. So again, as I said, these angles are very small. So tan of theta is nearly equal to theta. Therefore, tan of MON can be written as, so this angle is nothing but angle MON only. Okay, so this is correct. Are you getting me? The tan of these angles are considered to be very small. Therefore, tan of theta can be written as theta. Therefore, instead of tan of MON, simply I write angle MON, angle MIN, and angle MCN. Are you getting me? Okay. Okay, so we have to connect the relation between I and these angles here. So what we do is, now see here, if we take this particular triangle MO, okay, if you take this triangle MOC and triangle MOC, okay, so let me use the property exterior angle is equal to sum of interior opposite angles. Okay, so you can see here, if I take the triangle MOC, I am using the property exterior angle. In MOC, in this particular triangle, who is the exterior angle? Definitely I is the exterior angle. Exterior angle I is equal to, the exterior angle I is equal to what? I is equal to sum of interior opposite angles. You can see this one is the corresponding angle for I. Okay, so which are the opposite angles? You can see here MON is one angle which is opposite, and second is MCN. Okay, therefore exterior angle is equal to sum of interior opposite angles. So this one is MON and second is MON and second is the MCN. MCN. Is it correct? In a triangle MOC, I have used the property exterior angle is equal to sum of interior opposite angles. So these are the interior opposite angles. Therefore, I can be written as angle MON plus MCN. Again, what is MON? That is nothing but MN by NO. MN by NO. This is one particular angle, and second is MCN. That is nothing but MN by NC. Okay, so you have connected I with respect to other angles here, and these angles are connected with respect to distance. Okay, so similarly we have to okay, find the relation for r. So where is the r? R is here. Okay, so for that one, let us use the triangle MCN. Okay, so let me take the angle M. So let me take the triangle MIC. If you take the triangle MIC, for the triangle MIC, who is the exterior angle? You can see this. So this one is the exterior angle. MCN, angle MCN is the exterior angle. That should be equal to, which are the interior angles? Interior angles are MIN. Okay, so is equal to, the exterior angle is equal to MI1, and second is CMI. So this is equal to angle CMI plus angle CMI plus angle MIC plus angle MIC. So the required angle is the R. Therefore, I can write again, rearrange these terms here. So angle CMI is nothing but, you can write CMI can be written as angle MCN minus angle MIC. Angle MCN minus angle MIC. So what is MCN? It is known, and MIC can also be written as, notice here, this MIC and MI1 are shape. You are having the same angles. Are you getting me? MIC can also be written as MIN. Okay, because the angles are same. Therefore, it is MIN. So therefore, what is CMI? CMI is nothing but R. Therefore, R can be written as R is equal to MCN. That is nothing but MN by NC minus MIN, and MIN is nothing but MN by NI. MN by NI. Okay, if I call this one as equation number 2, this one as equation number 3. Next part is we have to substitute equation 3 and 2 in equation 1. Okay, so let us substitute equation 3 and 2 in equation 1. So therefore equation 1 becomes N1 into I. So what is I? I is nothing but Mn by No. Okay, plus Mn by Nc. That should be equal to what? That should be equal to N2 into R. N2 into R. R is Mn by Nc minus Mn by Ni. Okay. So you can see here throughout Mn is common. Okay. If you take the Mn on the other side, outside the bracket, and you can see that this Mn particular term, it get cancelled out. So therefore you can write like this. So therefore if the formula can be written as N1 by, okay, so N1 by No plus N1 by Nc is equal to N2 by Nc minus N2 by Nr. So which is NO, NC and Ni? You can see here. What is NO? NO is nothing but your object distance. What is NC? That is nothing but radius of curvature. What is Ni? This one is image distance. Okay. So now what we do is we are going to substitute this known values. Before that, you know that in case of geometrical optics, what we do is we are going to apply the sign convention. Okay, we have to follow the sign convention, that is the Cartesian sign convention. There are various rules, sir. The rule number 1 says that all distances are measured from the pole. Who is pole here? P. But N and P are very close. Therefore, we are taken as the measurements are taken from N here. So, the all distance are measured from the pole. Number 1. Second one is if the direction of incident light and the direction of measurement are in the same direction, then that particular measurement is taken as positive. Otherwise, it is taken as negative. Okay, so let me check one by one. What is NO? NO. NO. What is NO? You can see here. NO. Okay, so NO is nothing but, you can say NO is nothing but U. NO is nothing but U. Whether I have to take it as positive or negative, you can see that. Rule number 1 says that the distance are measured from the pole. Okay, so this is your direction of measurement. Rule number 1 says that the all distances are measured from the pole. So this is the direction of measurement. And what is the direction of light? This is the direction of incident light. You can see here your direction of measurement and the direction of incident light are opposite. They are opposite. Therefore, this particular distance is taken as negative. Are you getting me? Therefore, your U is negative. Okay, so this is the direction of measurement and this is the direction of incident light. Both are in the opposite direction. Therefore, NO is negative. Next, let me go for NC. NC. So this is NC. So this is from, you are starting from the pole, you are going towards C. So this is your radius of curvature R, and you can see here your direction of measurement and direction of incident light are in the same direction. Both are moving from left to right. Okay, so your measurement is also from left to right and direction of light is also from left to right. Therefore, NC is taken as plus R. Okay, what about NI? You can see here NI. Next is NI. NI, again you can see here NI. So this is the direction of measurement. Okay, so pole, you are moving towards I, and this is your direction of incident light. So both are moving in the same direction. Therefore, your NI is also plus V. Okay, so it is based on the Cartesian sign convention. So therefore, let me apply. So N1 divided by NO. What is NO? It's minus U. Therefore, your formula becomes minus N1 by U plus N1 by NC. What is NC? It is plus R. So that is equal to N2 by NC R minus N2 by Ni, that is V. Okay, so it is correct. So therefore, finally, let me make one systematic arrangement so that we can have the values on the one side. So if I take N2 by V on this side, therefore this becomes plus N2 by V minus N1 by U, object and image distance on the one side. On the other side, let me take N2 by R minus N1 by R. Correct? If I rearrange the terms, so it becomes N2 by V, N2 by V minus N1 by U, that should be equal to N2 minus N1 by R. So this is the formula which connect object distance, image distance and radius of curvature with refractive index. So we have connected the relation between physical quantity, the geometrical quantity and the optical quantity. Okay, so now this is a very useful relation in the next discussion. Okay, so let me write in terms of sentence so that we can have this formula in various cases. Okay, so the value of N1, N2, UVR may changes. So therefore, okay, so let me write this mathematical formula in terms of sentence. What is N2? You can see here. What is N2? What is N1? So what is N2? N2 means this particular medium where the image is present. Okay, what is N1? N1 is the refractive index where the object is present. Therefore, I am going to write like this. What is N2? refractive index of image space. A refractive index of image space. What is image space? Okay, what is image space? Image space means the space where refracted rays are present. Okay, refractive index of image space. Okay, now this is a definition. What is image space? The space where the refracted rays are present. Okay, in that particular space, sometimes there may not be image. In real cases, definitely you will have the image on the same spot. But in case of virtual case, they appears to be diverging from that particular point. But actually, there is no images. There are no such kind of image. We call it as the virtual image. Therefore, what is meant by refractive index of image space? The space where refracted rays are present. Okay, refractive index of image space upon V, that is the image distance. Image distance minus refractive index of object space, refractive index of object space upon object distance, that is equal to, what is N2 by N1? Difference in refractive index. Okay, difference in refractive. We have taken a particular case here. Particular case where object is present in the rarer medium and you are going to get image in the denser medium. There may be reverse case also. Okay, your object is in denser medium and you can have the image in the rarer medium. Okay, in that case, definitely the value changes. Therefore, we are interested in the difference. Difference in refractive index divided by R. What is R? Radius of curvature. Radius of curvature. Okay, now this is an writing this formula in terms of a particular sentence so that you can easily remember this particular formula. Refractive index of image space upon image distance minus refractive index of object space upon object distance is equal to difference in refractive index divided by radius of curvature. Okay, by using this particular formula, now we are going to study about the refraction through the lenses. That is the core topic here. Okay, so which I am going to continue in the next class. Okay, so thank you for your kind attention.